Alright, here's a tricky physics question about sound. It involves two identical strings that vibrate in different ways. One has the first harmonic excited. The standing wave in that would look like this. It would vibrate up, and then a second later it would be down, and then it would be back up again, and then down. This is also called the fundamental frequency. Now the fourth harmonic is going to have three more nodes. So let's, I gotta go up each harmonic to figure this out. So this would be the second harmonic. We know that the nodes must be at the ends where the string is fixed. And in this case, here's a node in the middle where the string doesn't move. The fundamental only had nodes at the ends, it didn't have any nodes in the middle. But when the second harmonic is excited, it kind of goes back and forth between this form and this form. It comes up over here and down over there, and then it goes back up over here and down over here, and back and forth, and so on. Okay, that brings us to the third harmonic. It would have another node in the middle, so the standing wave might look like this. And then a second later it would oscillate and come down over here and up over here. And then the fourth harmonic would have one more node, so it would have one more hump. So it would also come up like that at the end. And if you look at this, you can kind of see that two full wavelengths are held in this length of the string between the places where it's fixed, because it starts with no displacement. We go up, go down, come back to where we started. That's one wavelength. Then we do it again, go up, go down, come back to where we started, two wavelengths. So if this is length L of the entire string, then the wavelength would be half L. And then if we look at the fundamental, the first harmonic over here, we can see that the wave vibrates, this standing wave here is equivalent to half a wavelength within the length of the string, because it comes up and then it also needs to go down and come back up to be a full wavelength. So the full wavelength would be this far, but within the length of the string there's only half of a wavelength contained. So that means that this fundamental wavelength here of the first harmonic is twice the length of the string. And I'm going to catalog what we know up here, and as we figure out what we know, we can get closer to answering our question. This question has to do with frequency. It says there's a 315 Hertz beat frequency. What that beat frequency is the frequency of the oscillation of amplitude of the resulting wave when the two waves from the two strings overlap. And essentially the important thing you need to know for this question is that the beat frequency is just the difference between the two frequencies that are played. So all this is saying is that the frequency from one string is 315 Hertz higher than the other. So since we know this beat frequency, it might be helpful to translate what we know about the wavelengths. We know the fourth harmonic wavelength here. To translate what we know about the wavelengths into frequencies. And we can do that with this little equation that we know, that the velocity of a wave equals its frequency times its wavelength. Solving for frequency, we get frequency equals velocity over wavelength. So when we, if we were to translate wavelength of the fundamental, the first harmonic, into frequency, we have frequency equals velocity over wavelength. We've defined the wavelength as 2L. And we can do the same thing for the fourth harmonic. And it's good to point out here the velocity is the same for both of these waves because it's identical strings, same tension, same density, same length. So in this case, the frequency is velocity divided by wavelength. The wavelength is half the length of the string. And I like it when we write that a different way. Instead of v over 1/2, just 2 times v over L. And the last trick that we have to do to help us solve this problem is to just insert these definitions for F1 and F4. Or, yeah, let's call this F4. This is the, in this case, this is the fourth harmonic. There could be a beat frequency between any two frequencies. So this equation for beat frequency is usually given as F1 minus F2, but in this case we'll call our variable F4. But anyway, I'm going to insert our definition of F1 in here, and then I'm going to insert our definition for F4 over here, and that was equal to 315 Hertz. And now we have an equation with the unknown we want to solve for, and a length that we know is equal to 1.91 meters. So now all we have to do is some pretty simple algebra. It would be helpful for us to have both of the denominators here being the same thing. So let's just rewrite this one as half v over L. Same thing, just written differently. And we can kind of group them together now. So we have this over L. And now that we have done that step, we can multiply both sides by L, like such. Except this isn't quite exactly right because I forgot the absolute value brackets. It was about to not make sense because we get negative 1.5 v over here, but the absolute value brackets make that a positive 1.5 v, which does make sense. And that length L over here was given in the question as 1.91 meters. And solving for v, we get 401 meters per second.